Hi everyone, thanks for joining us. I am your host, Pablo Gomez. I am part of the Encora team in Mexico, and today we are going to talk about Kotlin type system. Before I continue, I would like to remind you that you can follow us in our social media, which are appearing on the screen just right here. Don't forget this session is part of our Global Dev Week organized by Encora. Also, you can use the chat to leave comments, ask questions to the speaker, or just to say hello. Now, let me quickly share about this expert. His name is Bruno Avar. He's a software engineer currently working to make commerce better for everyone at Shopify. Bruno has spent the last 8 years building mobile applications with different technologies, such as native Android, Xamarin, or React Native. Over the years, he has developed dozens of apps, mainly focused on entertainment, commerce, and also education. He is also co-organizer of the Android community in Lima, Peru. And without any more to say, let's add our speaker to the stream.
Hello, Pablo.
Hi Bruno. Thank you so much for accepting the invitation to speak, and it's a pleasure to have you here.
Thank you so much. Happy to be here. All right, awesome. So, first, Pablo, for this introduction, I'll get started with the presentation. There it is. Right. So we'll be talking about Kotlin type system today. All right. Before that, I'll just give a brief introduction of myself. As Pablo mentioned, I work as senior developer at Shopify. I also want to mention that before coming to Shopify, I worked at Encora. I was a principal engineer on South America Encora company. So I'm very happy to be in this conference as well. You can follow me on my social networks. I use Twitter a lot, and I will be sharing some of the contents there. But you can also download these slides in this link here in case you want to revisit the content later. All right. So about the topic, about what we'll be talking about. We'll be talking about Kotlin. We will be talking about its type system. This is a talk that I actually I gave for the first time 3 years ago, and I think the nice part about this specific talk is that regardless of how many years have passed, many of the contents that we'll be sharing today are timeless. I mean, regardless of the evolution of the language, regardless of all these new features that Kotlin keeps coming up with, these are the basics. These are the foundations on which the language is built. So I'm sure that this will be very helpful for those that don't have this understanding yet. So without further ado, let's get started. So about Kotlin, Kotlin is a statically typed programming language as defined by JetBrains, the creators of the language. So we can analyze this by for these two specific words about statically typed. It's, as they say, it's typed. It has a type system, and it's also static in such a way that it's unlike other languages that it's dynamic. Once you assign a type to any construct, then it can be modified, and we'll be giving more examples about that during this presentation. So I'll be sharing some examples of these um, of some expressions in Kotlin, all right, and we'll be analyzing the type of each one of these. So first of all, here we have a declaration of a variable. In this case, it's a name, and as you can see, its type is a string, and a string is a class, all right? In this next line, we have a variable age. It's declared as an int. An int, it's a primitive type, all right? And here we have another variable, it's a list, all right? And what is a list? Well, it's neither a class, it's not a primitive type, it's an interface, all right? As you can see here, we have classes, we have primitive types, we have interfaces, which are different concepts, but at the end of the day, all of them are types that you can use within the language, all right? So something that I want you to understand about this talk is that classes are not the same thing as types, all right? This is like a huge important difference, and we'll be exploring during this session. So I hope that if you take something away from this, is that you understand this distinction and you know how to apply it when you are coding. All right. So now we'll explore a little bit of those types that are built into the language itself. So we have the logical types such as Boolean. We have integral types, byte, chart, int, long, floating points such as float and double. We have even structure types, arrays, strings, and even function types that come within the language. Um, we also Kotlin also have some special types, which are any, are nothing, and unit, and we'll be exploring each one of these during this presentation. All right. So the same way that Kotlin comes with its own types, that you don't have to do anything to have them available, we can also define our own types by writing our code. All right. So we can declare classes ourselves, we can declare interfaces, we can declare custom enums, and so on. All right. So by declaring these constructs, we are able to create new types that are available for us while writing the code. But we can even combine these concepts with things such as function types, generics, and nullable operators. And we can create even more types, and we'll be giving some example of this. All right. We'll go and take a look at the hierarchy of types. All right, because at the end of the day, types are constructed as a hierarchy. Um, but before going into Kotlin ones, let's take a look at Java's hierarchy type, because they are very, very related. All right. So this is like a simplified version of what will be a type system hierarchy for Java. All right. In Java, we have the object, which is basically the super type of every single other type out there. Even if you don't explicitly declare it, that's how it works. All right. So for example, if we have the integer class, it extends from number, and number extends from object. You have the string class, and that's um, inherits from object. You can even declare your own classes, like your subclass. You can declare your own class, and even if you don't explicitly write it down, it will also be a subtype of object. All right. So we have, this is how it works in Java. Um, so how different is Kotlin? All right. There are two main differences in terms that rather than having object at the top, we have the type any. All right. And even also there's something else, that is that we have nothing below everything. All right. And we'll be exploring both of these new concepts. Now, so let's focus on the one at the top. So, but making the comparison between the Java version and the Kotlin version, my question is, do you think is any equal to object? Now, let's give some let's take a look at some code to kind of find out the answer to this question. Um, let's say that we define a function, all right, such as this. It's a testing function. It receives a parameter, and it's of type any. All right. This is how we write it on our code editor, but we can take a look at the bytecode that this generates. So we'll take a look at how the virtual machines sees this specific piece of code, and it gets translated into something like this. All right. So we'll focus on these specific parts. If we take a look at the bytecode, we'll notice that at the end of the date, when you declare a type any, it gets translated to an object type. All right. So this is how it's represented at a more lower level. So now, if we, for example, go back to Java and we write this variable as this, we can declare a variable that is of type object, and we can assign it null, right? This is perfectly fine. And actually, null is the default value for all objects that are not initialized, all right? So this is perfectly valid in Java. So if we take the assumption that object is equivalent, any of the is equivalent of object, and we try to do the same in Kotlin, so we create a variable, we say it's type any, and then we assign null, then we will notice that this is actually not allowed. All right. And why is that? It's basically because in Kotlin we have something that is called subtyping by nullability. Right. So we have a type any, and we have a type any optional, and these are different types. All right. And actually any is a subtype of the of its optional counterpart. So if we go back and see the hierarchy that we used to have below any, we actually have the same hierarchy for its optional counterparts. So the same way we have any optional, we have number optional, we have integer optional, we have string optional, but it doesn't even stop there. You can go even one step further, and we know that the actual hierarchy of types here is that an int is a subtype of its int optional counterpart, and it's also subtype of number optional, and so on. All right, so the hierarchy can get very complicated when you start mixing it with optional types, but this is how the language itself is built and how it will get translated when you start working on your code. All right. So as you can see, we can maybe declare a single subclass here, but at the end of the day, the end result is even more types. All right. So when we are defining a class, such as a custom class here, we automatically have two types available. So we have a type which is optional and a type which is not optional. The optional is the one with the interrogation mark at the end. All right. Uh, so once again, one single class, two types. Um, and this is given that we are combining our custom class with the nullable operator. So this is what I meant when we combine these concepts, we can create even more types, right? And this is because of the type typing by nullability. Now, we have one class, two types. However, those two types are available only while we are coding, right? Um, because after compilation, this non-nullable concept that we used to have no longer exists, all right? And to see that, we will go back to the example that we had before, in which we declare an any parameter, and we go to see the bytecode. We will notice that it's written down as an object, all right? It does have some annotations and some specific code regarding checking for not null, but at the end of the day, it's an object type, right? And if we see the counterpart with any optional, we will notice that the bytecode is pretty much the same, all right? We no longer have the null checks, but it's still represented as an object. So this is something that only exists at maybe while we're writing out code, but at compile time, it's exactly the same. So this is a concept that no longer exists after compilation. All right. So if we go back to the question, is any equals to object? Well, the answer is actually that the exact equivalent will be any optional. So any optional will be the equivalent of having an object type in Java, right? Um, so we'll be moving on to the next topic, and it is nothing. All right. So what is nothing? Nothing is basically, as we saw in this diagram, it's a subtype of every other class that we have defined in our program. So this is done automatically, as you don't have to declare a nothing type. It's done already for you um, uh, by the language itself. So basically, nothing is a type that never returns a value, right? And its main use is for control flow. We'll see some examples of that. Um, so here we have a class, all right? It has properties, a name and a last name. Both of these properties are optional. As you can see here, it has the question mark, so it can have a null value, all right? And now we have a function that validates the data, which basically says, we'll take this data, which is optional, we'll try to extract its name, but if its name is null, then we will be returning false, because we know that the data is not valid. We will apply the same logic to the last name, and then we'll validate if this name is not blank, and if this name is not blank, then it has valid data. All right, super simple. It's basically verifying that data has any content. All right. But let's focus on each one of these lines. Let's focus on this specific expression, all right? So let's take this and analyze it part by part. But before doing that, as you can see here, I'm not declaring the type of the variable. I'm declaring just val name. I'm not declaring the type, and this is because Kotlin can infer the type of each expression, all right? So what is Kotlin inferring? What type is name? All right, so I'll give you a few seconds to think about it, because we know the data, this is optional value. This is an optional string. So what's the type for this expression? Actually, the type is string. It's not a string optional, it's a string. All right. Um, so this is the type that is inferred, which kind of makes sense given that we know that this thing at the left is a string, optional, yeah. But we still have the question about, all right, so if this is a string, why can we assign a value that is return false? Because this is a Boolean, as you know. So how is this happening? How is this possible? All right, how is it possible to assign return to a variable? Even more so in this return value that has a Boolean. All right. Um, so this is possible because in Kotlin, mostly everything is an expression. All right. And this is something that is one of the key differences with, for example, Java, in which things are not real expressions. So we'll see some examples of how this plays out in action, even in other concepts within the language. All right. So for example, when we are using a when expression, which is the equivalent of a switch for those who haven't used it before, um, when you're using a when expression, you can actually assign the result of that when expression directly to a variable, right? Um, and it can infer a type. This expression itself has a type. Which one it is? It's a string, right? Because we're returning a string value for each one of these expressions, all right? If we can even do this with an if else, all right? Because we can say, all right, we analyze a number, then it has this message, otherwise it has this other message. Um, and in both cases, uh, this return a string. So what's infer type? It's a string itself. It's the result of this whole expression, right? In Java, you can't do this because if it's not it's not an expression, so you can maybe return this value, but you can assign it to a property, all right? But you can in Kotlin because this whole block, it returns a value. And even you can do that for functions because you can declare a function and then assign it to a variable. And that's also possible. And what's infer type in this case? Well, it's basically a function type, all right? And maybe we'll talk about that later, all right? Now going back to the line that we were analyzing, what is happening? Why is it possible to assign a return variable here? This is possible because this expression is returning nothing. Like the return expression, regardless of what you're seeing here, that it returns false, this expression itself, like when you write this down, that returns a type as well, and that type is nothing. All right. So we have here that on the left we return a type that is string, and on the right we have a type that is nothing. All right. So if we go back to the hierarchy, we know that nothing is a subtype of string. So this is, we have a relationship here. Uh, and this is actually something that is allowed in object-oriented programming. And you can even uh, go back and refer the Liskov substitution principle to kind of validate this behavior. Because the principle says that if a subtype S is a subtype of T, in this case, is if nothing is a subtype of a string, then the objects of type string may be replaced with objects of type nothing. All right. So this is true because nothing is a subtype. Uh, and one very important part about this principle is without altering the properties of that program. Um, so given an example here, if we have a hierarchy like this and we have a fruit and two subtypes, um, we can assign either value, either an orange or an apple. We can even take a function that receives that fruit. We can pass it either instance, and it will work, and we are keeping the principle in place. So that's also why applying the same logic, this is how it works. Um, it works because we have a string here, a subtype on the right side. So this the compiler can make this work. All right, you are actually assigning a valid value to this name. So this is how this is even possible, right? You can even take it a step further, um, and you can say we have a name of type string and its value is return false. This is perfectly possible, all right? Although it doesn't really make much sense, but this is something that can happen, and this is allowed because of how the type system works. Um, Now, going back to the question that I was asking, how is it possible to assign return to a variable? This is because nothing is a subtype of everything, and you can assign that value to any given expression. Now let's analyze something else in terms of seeing more practical usages of it. Um, throw, the expression throw also returns nothing. So we can replace that return with a throw here. And this is actually a very common practice in a lot of code bases. Using an else operator like this, and then using a return, or then using a throw. This is something very common, and this is also supported because throw itself returns a nothing expression. How can you even use it further? We can see an example of this being used in the Kotlin standard library, right? Um, Kotlin standard library defines a to-do function. And if you see the declaration of it, you'll see that the return type of this to-do is nothing. It's literally written down like that. And its value is a throw, not implementation error, all right? Um, so why is this useful? Um, Basically, for example, let's say that we are writing a a function, all right, and we use the to-do function that we define above, and then we try to return something, all right. As you can see here, the IDE will basically give us a warning, and it will tell us this piece of code that you have declared here, that is unreachable code. This is code that will be never executed. And you may start thinking, hey, but why is it never executed if we know that, like, when you are executing code, usually it goes line by line, right? It executes this expression, then it goes to the next line and execute it. But how does the compiler know that this will never happen? uh, this is because the compiler knows that after nothing is returned, then the execution flow cannot be continued, all right? And if we go back to the example, the compiler here knows, if we are making a return false in this case, uh, the compiler knows that given the type of this is nothing, then whatever comes next, whatever expression that gets analyzed further, won't be actually executed, all right? Because we're ending the statement here with the return, all right? So this actually will never, ever, ever get assigned to name, all right? Because execution stops there. And that is something very, very smart. And this is actually, I'm impressed by how they designed it, because this is all because of how the type system work and having this nothing type underneath the hoods, all right? Um, so the same way that Kotlin uses for the to the function, you can even define your own. We can say declare a forever function that it's of type nothing and it's an infinite loop. All right. Given that we know it's an infinite loop, then if we use the forever function, the compiler knows that for whatever in under any scenario, this code will be executed, because we'll be stuck on the previous line because it's never ending. However, if we change the condition here and we change it to false, then we know that this condition will eventually end. So the compiler knows that, um, and then it will say, hey, I know that this is will actually end, so this will have a return, this will continue its execution. And if you want this to continue its execution, then you can have a type nothing as return value, right? So what should we have? I mean, we should be returning nothing. So what do we do here? All right. So in this particular case, you say, all right, if the return type is nothing, then let's create an instance of nothing. However, it is impossible to do that. All right, you can't create an instance of nothing. That's forbidden by the language itself. You can try to return null, but null is not exactly the same as nothing. Um, However, null is an acceptable value for nothing optional, so that's something like a workaround. Um, but if you make this optional, you are no longer, the compiler no longer can make assumptions about the code, so there's not going to be warnings. So basically, this is useless. I'm just adding it here to make you realize the difference between adding optional and nothing. This is the one that is useful for the compiler. This one, not so much. All right. So now let's take a look at some pieces of code, um, and I'll be showing you some examples, and you'll try to kind of figure out what's the result for each one of these expressions. All right, so let's say that we have a function that is called print. It has a value that it's of type any optional, and depending on the type of the value, then it's gonna be outputting a different text. All right, so if we call this function with a message, what do you think is gonna be the end result, like the output to the console? It's gonna be text message because it's going through the first case. If we call it with this, with a 10 as value, then it's gonna be outputting the second case. All right, if we call it with false, then what is it doing? Well, it's gonna be giving an unexpected value of false. All right, because it's neither a string, it's not an int, so it's going through the else. What if we pass null to this value? Well, in this case, the output remains the same. It's going to the else, right? But let's say that for one reason we want to have a separate case for null, right? And we want to say if it's null, then we want to output this message. This is actually not allowed, and you'll get an error if you try to validate by null, right? And this is because something that I want you to take away from this is that null, it is not a type. All right, it does not represent a type. Null represents the absence of a value, but it's not a type. All right, it's something that you can assign to an optional type, but it's not a type itself, so you can't validate against it. So what can you do in this case? If you may want to make sure that this if you want to make through this case, well, you can use nothing optional. It's going to be like the safest way of validating null in case you want to validate a type. So this will work, and it's actually this is going to work, and it's going to output the value that we expect. So basically what we've been seeing here is that we can define types. We can combine all these concepts, classes, interfaces, enums, and combining with the nullable operator, and we'll have a lot of new types available for us. All right. Now let's talk about generics. All right, it's going to be the next topic that we'll be discussing here. For those that have never heard about generics, generics are basically those things that you can see between the lower and the higher tags. All right, so here, for example, we have a response with a generic type T. All right, so for every time we define a response T class, this is actually not a type itself. All right, like in its generic state, it's not a type. However, it becomes a type when we combine it with other types. Or for example, if we declare a response that is type integer, this is a type. If we declare a response that is type boolean, and then this response itself is optional, then that's another type. All right, and you can even make as many other combinations as you want. We can actually have infinite types by declaring a single generic. All right. However, now let's revisit this concept. One singular declaration of a generic concept. However, we have infinite different types available for us. Right. So making the distinction there, but these are similar to what we saw before. These are only available while we are coding. All right. Because after compilation, after we compile our code, the generic type is erased. And this is called type erasure. In case anyone has ever come across some kind of issues regarding that, maybe you are doing some kind of compile time verification of the properties of a type, then maybe you may have come across this. This is why. All right, after compilation, the generic types are erased, and that's called type erasure. All right, and we'll see an example. All right, let's see that we have a class that is response. It has a type, a generic type. And when we have a function that when you run it, it will try to print the type t, right? So this is what we want. It seems like a pretty simple piece of code. We just want to, at runtime, we want to print the type t. Uh, However, this is going to throw you an error, and it's going to tell you you can't do that. You can use t as verified parameter. Try to use a class instead. Um, so this happens because the type is no longer available. I mean, when you run your code, when your code is actually executed and running on a computer, on a phone, or whatever other place, the virtual machine no longer has this information for you. So it has been completely deleted. It's not available for you to use. So for this exact case, there is no workaround. This is something that you have to deal with, and something that you have to take into consideration when dealing with um, generics. There are some data that you won't have available if you're dealing with this because of type erasure. Um, we can make some changes, so we can make it an uh, independent function. Instead, we can pass it the response as a parameter. We can also use generic here. Um, we'll still be getting the same error. However, we can make a small change here that is called an inline verified. Uh, and after making this change, then we'll get no error because this value has been inlined. Uh, and this is a concept that I will not be digging into, but something that you can keep exploring. All right, this is basically the only way in which you can work around that issue that we were seeing. This is basically because the value is inlined, and rather than being deleted, and the type erase is basically something that you're putting in place so the information is still available for you. All right, so this is going to be homework in case you want to explore more about it. Now let's talk about hierarchies. All right. So let's say that we have these hierarchies. We have a fruit, all right, that is a superclass, and we have an apple and an orange, which are subtypes. All right. Um, and let's say that we declare a class that is a box of things. So basically here you can have whatever, right? So you can have a box of fruits, all right? You can have a box of apples, and you can have a box of oranges. So if we have this hierarchy at the top, then we will expect this to be the same, right? So to be preserved for generics. However, that's not true. That's actually an assumption that we cannot make because it's wrong. Um, because in reality, the type hierarchy structure is like this. None of them inherit from one or the other, all right? They're completely independent, so you can not make any assumption about inheritance. This is because of a concept called covariance and contravariance, which I won't be digging too much into, all right? But basically, to work around this, we have some additional expression, which in this case is out, all right? In which you could say, basically what this means is, um, we have a box which can only output this type T, all right? So we have a box in which we can only take away fruits, then a subtype can be a box of apples and a box of orange. But that's because we are telling the compiler it can only output this, so it can make the right assumptions and create the specific time of hierarchy, all right? We can also make a change, and rather than using out, we can use in, and the hierarchy is reverted, all right? Because we know these are a box in which you can put in this type of data. So you can take a box of apples, and you can put in fruits, you can put in oranges, and the relationship is reverted, right? But this type hierarchy, we are the one that are in control of it. If we give the compiler enough information to kind of um, realize how it can work around itself, then it will be able to make the changes to the hierarchy and make the right assumptions. But we need to give the compiler some help to figure this out, and we do that by using the out and in keywords, right? And as you can see here, we have already discussed these concepts, combine them with generics, and we know have a lot more types, right? Now let's This talk in this talk we have already talked a lot about a lot of things. So I don't want to put too much into your plate. I know this can be a lot of information if you have never heard about type systems. So probably worth another session. Maybe you can explore more about function types in a separately. So we won't be discussing it here. However, something that we will be discussing before ending this talk is the unit, which is the one that we are yet to review. All right. So how does unit fit within this hierarchy? We have any at the top. We have nothing at the bottom. Unit is basically a subtype of any. All right. You can inherit it. It's a final type, um, but it does inherit from any. All right. How is it declared? It's basically an object, a singleton called unit, and it has a string method. That's it. That's exactly what unit is. Um, and how is it used? Basically, every time you define a function like this with no return type, the actual return type is unit. All right, but it's implicit. I mean, here it's implicit. You don't have to declare it, but these two expressions are exactly the same. You can either define it or not, but they are exactly the same, and it's equivalent to the void expression that we have in Java. For those that, although void is not really a type, but unit is, right? So similar, but not exactly the same. Um, so either of these expressions in which you use unit, uh, usually they are created because these are not pure functions. Rather than returning a value, these are usually functions that have some kind of side effect. All right, and this is something that I want to dig into before um, finishing the talk. What's I'm going to talk about pure functions. All right, pure functions are basically functions that, given an input, it always emits the same output. It's a function that has no side effects, and it's a function that is very, very unit testable, right? So, for example, if you are creating this function in which you take two parameters, and then you add them up, this is a completely pure function. For every set of inputs, you will always have the same set of values. Now, if you add a random value here, a random component here, then this is no longer pure because you can send the same values in two consecutive calls and get different results in each one of them. So it's no longer pure. Uh, you can maybe return the same values with no random component, but then you're printing stuff. When this is a side effect, because rather than only returning something, it's also performing some additional kind of operation. So this is not exactly pure. Uh, Maybe you can even be updating the database here. This is something that happens in a lot of code bases. So I'm not saying that you should always use pure functions or not. Um, I'm just saying be careful of it. I mean, make sure not to abuse side effects. I make sure to make your functions as uh, testable as possible. And this all goes back to using unit in the right way. Right. So some additional study material, you can explore this talk if you want to. It's given at a Kotlin Conf from quite a few years ago. Uh, you can explore the difference between classes, types, and objects in this other resource. You can explore covariance and contravariance in Kotlin using this other blog, um, and you can even keep digging more into those kind of concepts that we have not talked much about. So that's it for the talk. Um, Thank you so much. I hope that I know that this is very dense concepts for those who have never heard it before. So I hope people were able to follow along. But yeah, if you have any questions, feel free to reach out. And if you want to revisit the presentation, you can find the slides here. All right. So thank you.
Wow, thanks so much, Bruno. It was an amazing session. We are just on time for the next session. So if you have any question, Bruno's social media are available for you, right, Bruno?
Mhm. Yeah, you can write me
Okay.
down on Twitter. Yeah, I usually very active there, so feel free to do that. I'm happy to answer any question about this topic. Yeah.
Thank you so much, Bruno. Thank you so much, everyone who is watching this. The next session is starting now, and remind that you can copy and paste the link appearing in the comments for the next session. My name is Pablo Gomez. Keep enjoying this event and see you soon. Bye bye.